Week 7 covers system equations and inequalities, as well as partial fraction decomposition and linear programming, as well as some of the methods to solve the system equations and inequalities. Start off, we're going to go over systems equations. Here you can see two equations. A system equation is simply a group of equations, in this case 2, sometimes 3. This helps find the value of one or more variables in the equation. As previously, you're only limited to solving for one of the variables. The equations can be linear, which are straight lines, nonlinear, which are equations with higher terms, x squared or x to the third. The equations are more equations, like I mentioned here. As we can see, we have 3 equations, or again, nonlinear equations. In a system with 2 variables, we can use one variable to find the value of the other variable. This is typically referred to as the substitution method, as we take one variable and substitute it for the other in the solution process. I'm going to go over some examples of each method to help you understand, I guess, the process of finding the variables using each individual method. Substitution, we're going to use 2x plus y equals 5 and 3x minus 2y equals 4. Again, 2 equations, 2 variables, that means we can solve this equation. Using substitution, like I said, we need to find one variable just by itself and use it in the other equation to solve the other variable. So first, we got to figure out which variable do we kind of already have by itself, or what can we get to by itself pretty easily. In this equation, you can see that the y is already no coefficient and can pretty easily be brought to by itself. So we do that by moving the 2x to the other side to get y equals 5 minus 2x. Now, substitution. Again, I'm going to say this a lot. Substituting this little expression for any time we have a y. Now, we use the first equation to find that expression, so we're going to substitute it into the second equation. Now, you always have to do that using substitution, is substitute the variable you found into the other equation that you did not use. So I do that right here. I bring down the y, plug it into equation 2. We get that right here. 3x minus 2 times that quantity that we'd already solved for, that 5 minus 2x. We get 3x minus 10 plus 4x equals 4. By distributing the 2 into each term in the parentheses, combine like terms with the 3x and 4x, we get 7x minus 10 equals 4. More simplification, 7x equals 14, x equals 2. Now, we have one of the solutions. We have x equals 2. We can bring that right back into the equations, either or, doesn't matter what we plug it into, but I said we plug it into this one and solve for the other variable. Plug in that 2 for the x. 2 times 2 plus y equals 5. 4 plus y, again, combine like terms, we get y equals 1. So here we have both x and y. We solved for x, substituted it into the equations again, and we got y. That is the substitution method. Now, another pretty easy method for solving system equations is graphically. Now, in this video, I won't specifically show you how to graph equations, as I'm going to assume that you know how to do that. But it's pretty easy to see when a system has a solution or resolution by looking at the graph. In this case, we know the solution to the equation to be x equals 2 and y equals 1. And that manifests in the graph as the intersection between the lines, 2, 1. It's as simple as that. If the lines cross, that is a solution to the equation graphically. Now, this also works again for multivariable equations. 3 lines, they all intersect at one point. That's the solution to the equation. As well as nonlinear equations, we can see the intersections is a solution. In this case, we have 2 solutions because there's 2 intersections. The next method we'll be going over is elimination. As the name suggests, we'll be eliminating one of the 2 variables to get it by itself, find the value, and then plug that back into the other equation. It is similar to substitution, and then to find one and plug it back in. But in this case, we'll be eliminating. We'll be striking out one of the variables. I often call this the squishy method because we'll be taking 2 of the equations, either adding or subtracting them, squishing them together, eliminating one of the variables, and finding the solution. Here we have 3x plus 2y equals 4, 5x minus 2y equals 12. The strategy for elimination is to find some sort of multiple of the variables where when you add or subtract them, they're most likely going to be 0. This one is very easy because we don't need to find multiples. We just have positive 2y and negative 2y. If we were to add positive 2 and negative 2 together, we would get 0y and eliminate the y. If in other cases where this where the variables aren't exactly the same number, you can multiply the equations by some sort of number to help achieve that situation where the coefficients would be similar, right? So if we multiplied this whole equation by 3, every coefficient we multiplied by 3. So this would be 9x plus 6x equals 12. And then you can squish them together. But in this case, we don't need to do that. Here, we see that we can add the equation together, like I mentioned. Positive 2 plus negative 2 would equal 0, eliminating a variable. We also need to do that with the x's and the constants over here. 3x plus 5x, 8x. Positive 2 plus negative 2, 0. Eliminating the y, 4 plus 12, 16. Simplifying, we get x equals 2. One of the variables is already solved for. Now plug that back into the equation, any of the equations again, and just find out the y. So I do that here. Plug in that 2 for x. 5 times 2 minus 2y. We get y equals a negative 1. So the solution of this equation would be x equals 2, y equals negative 1. Again, that was a pretty equation. Let's use do a little bit harder one where we need to multiply or find multiples of the variables. Here we have 4 and negative 12 and 7 and 1. Now again, the strategy here is to find two numbers that you can find multiples of each other pretty easily. 7 and 1 are pretty easy, right? Because you can multiply 1 by anything to get 7. But I also feel that 4 and 12 are pretty easy, right? 4 times 3 is 12. Again, a simple multiplication to get to 12. So let's do that right here. So we're going to multiply equation 1 by 3. We multiply everything in the equation by 3. So equation 1 multiplied 3 gets us 12x plus 21y equals 60. And then we can, again, add that to equation 2, squish them together, and eliminate the x term. We get 20y equals 80. Easy simplification shows that y equals 4. Plug that right back into the equation. Simple algebra, we get x equals negative 2. Pretty easy stuff to find the solution using the elimination method. You can also solve system equations that have more than 2 variables, but as I mentioned before, if you have more than 2 variables, you need more than 2 equations. Typically in this class, you'll have 3 equations and 3 variables, so I'll be doing that for the remainder of the multivariable linear equations that we're going to see. The first method for solving those equations will be back substitution. Now, back substitution is a little bit of a cheating method because in the cases where you can use back substitution, the equation is pretty much already done for you. Now, here we have 3 equations. And as you can see, it's in this sort of diagonal orientation where we have just one equation with x's, and then an equation with just y and z, and an equation with just z. Now, you might be able to tell what we're doing here, but since we already have z, we can just plug in z from 3, plug it back into 2 to find y, plug that y and z back into 1 to find x. Simple as that. It's pretty much the substitution method, but going backwards from 3 to 1. Let's see how that works. Of course, equation 3 already says z equals 5, so let's plug that into the second one. Y plus 3 times 5, we get positive 15. Subtract it over, we get y equals negative 10. Already we have 2 variables already solved for, so we can plug z and y back into equation 1 where we have all the variables. Simple algebra here. Again, x equals negative 24. Substituting it backwards along the process, we can get all 3 variables using back substitution. Pretty simple method there. Now, as we get a little more complex with the equations, we can't necessarily use back substitution. Most of the time, you're not going to have a variable right off the bat equaling something else. So in those cases, we can use Gaussian elimination, which again, as the name suggests, is just like the elimination method we did earlier, but we're going to do it a couple times to keep squishing down the equations to get the same sort of orientation that we had with back substitution, where we had the equation in a sort of diagonal orientation, because then we can, like we did before, just use z to find y, y and z to find x. So we need, I guess, to satisfy this sort of orientation, we have one equation with all 3 variables, one equation with 2, and one equation with 1. And we're going to use this sort of checklist box to keep track of how we're doing all along the way. You don't need to do this, but I think it helps me keep track when I'm doing it. So here we have a system of equations. Equations 1, equation 2, equation 3. As we mentioned, we do need to get this orientation, and as you notice, there's no more x's in this column. So what the first thing I'm going to do is to try to eliminate all the x's in this column using the elimination method. So let's focus on all these coefficients and figure out a way to squish some of them to make new equations that don't have x's in this column. So the first thing I see here is pretty easy. We see positive 1 coefficient, negative 1 coefficient on these two equations. So let's squish them together, and this will almost certainly eliminate one of the x's. Here we have the two equations, positive x, negative x. That eliminates to 0. Negative 2y plus 3y, we get 1y. Just a 3z here, we get 3z. So we have y plus 3z equals 5 as our final equation. Now, as you notice, this satisfies the yz equation. So we can check that off too and just replace our second equation with this one. So now this is our new second equation. So now we have one equation 1 with 1, 2, 3. In the beginning, of course, you're always going to have an equation that already has all three, so we can check those boxes too. So we have equation with just y and z, check, check. Equation with x, y, and z, check, check, check. As I mentioned, we replace equation 2 with that equation that we found. So we have our new 3 equations. We still have an x left in this column. Let's try to eliminate that. These are the only 2 x's, so we need to find a way to squish these two together to eliminate one of the x's. I did that by multiplying equation 1 by negative 2. That gets us negative 2x and positive 2x. When we squish them together, it's going to eliminate the x, and that's exactly what it does. These go away. These add to negative y. These add to negative z. This adds to negative 1. So in the previous step, we already satisfied this yz equation. So even though we have yz in this, let's keep squishing to try to get it down to just z. So I have negative y, negative z. We need some sort of equation that we can combine to eliminate preferably the y to get the z at the end, right? And as we look up here in our new 2 equation, we have exactly that, an equation where we can combine together to get just a z. So I did that. I brought down our new 2 and combined it with that yz equation that we found, squished them together. Again, pretty lucky. It just happens to eliminate the y by itself. These go away. This negative z and positive 3z becomes 2z. 2z equals 4. Make our lives easier, divide by 2. Z equals 2. So now again, this z equals 2 satisfies this just a z equation. So we don't need to do anything more. We can now use back substitution to solve for the other y and x variables. When I put all our new equations together, we have that sort of diagonal orientation that I was talking about. Clearly, we can use back substitution now. Z equals 2. We can plug that into the first or the second one. Plug that into the first one again. So here, I show the process there. Where solve for the y, get the y. Solve for the x, get the x. Now that's Gaussian elimination. It's pretty much using the elimination method previously a couple times to end up finally doing the back substitution method. The next topic we'll be going over is partial fraction decomposition, which is used to take big nasty fractions like this and break them down into bite-sized pieces. We usually use partial fraction decomposition when the denominators have quadratic equations or either high term expressions that we don't really like to work with, especially in the denominator. We can break an equation like that into smaller pieces with the factors as the denominators. Now this assumes that you know how to factor, especially some tricky factoring equations. So I'm going to use the big X method, and if you need some review on that, I also have a video reviewing the, quote, big X method for factoring. So to help you get some practice, I'm going to go over a partial decomposition problem. We're going to break this fraction into smaller bite-sized pieces. The first step in partial fraction decomposition is to factor the denominator. Here we just pull it out so we can look at it. Quadratic equations have 3 terms, a, b, and c. It's just that a is coefficient of the first term, b is coefficient of the next, and c is coefficient of the last. Using the big X method, where we take the a multiplied by the c and take the c, we're able to find the factors using the big X method. Again, I will have another video reviewing the big X method also on this playlist. Using this method, we get the factors 2x plus 1 and x minus 1, which will be the denominators for both of our fraction pieces, right? So now that like I said, now that we know that those are our fraction pieces, we can just throw them under 2 fractions and put an arbitrary a variable and an arbitrary b variable on top. So now we have our starting fraction and our 2 pieces. Now, of course, we can't end here. We need to figure out what a is. We need to figure out what b is. So we got to set these 2 sides equal to each other and solve for a and b, right? Using our system of equations solution methods. Now, to get them in an even playing field, let's try to get them out of fraction form. Of course, we get out of fraction form by cross multiplying. Right? So we multiply the denominator by the numerator over here, denominator by our numerator, and the two denominators. Now, we already know what the two denominators multiplied are because we factored this. So we know it's just going to be this. So right here, I have that step where we have the cross multiply a times x minus 1, b times 2x plus 1, and the bottom. Again, we know that these two denominators are the same, so we can just cancel them out. Boom, boom, and get a super easy x plus 5 equals a times x minus 1 plus b times 2x plus 1. Now, like I said, we know that the denominators of these are going to be the same because we factored it. So when you're doing it yourself, honestly, when you get to this step, you can just skip all the way to this step. Just make sure you multiply a by the other denominator and b by the other denominator. So you can just skip right to this step, honestly. Now, we're going to be using a sort of elimination method where we want to eliminate just the a or just the b, and then we can solve for them. In this case, we're not going to be using a system of equation, but we're going to be picking a number for x, any number we want, preferably one that eliminates one of the two. In this case, I'm going to eliminate the a. So how do we eliminate the a? We should probably make the coefficient 0, right? Because 0 times a is 0, and that just gets rid of it. So how do I make this coefficient 0? In this case, I just put 1 as the x, so 1 minus 1 equals 0. So that's what I'm going to do. I'm going to have x equals 1, and for every x, I'm going to plug in 1. And that's exactly what I do. 1 plus 5, a, 1 minus 1, that goes away. Plug in the 1 over here to get 6 equals 3b. Right off the bat, we now have b solved for, and we can use that, or we can't necessarily use that to plug back in, but we're one step closer to the answer. We do the same sort of process as we did with a, where we need to find some sort of coefficient here to eliminate the b. In that case, I use negative 1/2 because negative 1/2 times 2 is negative 1. Negative 1 plus 1 is 0, right? We're just trying to get the coefficient here to be 0. And that's what I did with negative 1/2. We plugged negative 1/2 into all the x's. I did that here. Simplify, I get 4.5 equals negative 1.5a, and just solve for a to get a equals negative 3, and b was 2 from earlier. We just plug that back into our a and b as we mentioned earlier, and that's partial fraction decomposition. Now, the individual steps can be a little intimidating, but you just break it down piece by piece by piece. It's actually not that bad to turn this into this. Next topic we're going to cover is system of linear inequalities and linear programming. Now, a system of inequalities is just like a system of equations, except for the equal signs are replaced with inequality symbols. And the graphs we're going to graph are going to look just like we have seen plenty of times. So here we have the system of inequalities, right? Three equations with inequality signs. And again, like I said, they're just like regular equations. We can solve them like regular equations too. I solve that first equation, I would get something like this: x minus 2 equals y, and we have a graph just like this. But if I were to graph it as an inequality, we'd get something like that: a dotted line with a shaded region. Now, not all inequalities will have a dotted line. That corresponds to the specific symbol. In this case, we have a less than symbol, which is dotted line, and a less than or equals to symbol, which would be a solid line. Now, the dotted line just means that there are no solutions specifically on this line. They're all above it in the shaded region, where a less than or equals to symbol, like this, is a solid line because that means there are solutions on that line. So I guess make sure you know what line corresponds to which inequality symbol. So again, I'll show these equations, which again look like we've seen before, 3 simple equations, and then I'll show you the inequality versions, right? And we see these shaded regions. I'll specifically show this one. Now, x is greater than negative 2. Now, that means greater than in the positive region is a solution. All x's that are greater than negative 2 will be a solution. So all values in the shaded region are a solution to this inequality. And on the flip side of the coin, we have a less than. All regions below this line are solutions to this inequality. Pretty simple stuff. And then if we have all of them together, a solution to the system of inequalities would be in the shared shaded region, right? They all shade this specific triangle. So all solutions in this triangle would be correct solutions, right? So 0, 2 would be a solution, but 0, 4 would not be because it's not also in this green area, despite it being in this blue and red area. Linear programming is kind of like using all of the previous things we mentioned to either optimize or minimize a function. So here we would have a function, this 5x plus 7y equals z. And we want to find the highest value of z or our lowest value of z. But we want to make sure that high value of z or that low value of z also falls within our constraining area. Now, a constraining area is the product or the result of a system of inequalities. A question would give you a system of inequalities and an equation we need to optimize or maximize or minimize. Graphing these equations is pretty easy, even by hand. So I skipped that, and I have all these equations graphed for us. Now, one thing to know about linear programming is the maximum value or the minimum value is always on the vertex, right? If we want a line to be at the highest value, but also go through here, we want it to maybe just barely go through here because this vertex is the highest point. Or if we want it to be the furthest forward, this vertex would be the furthest forward. If we want it to be the lowest, then maybe this vertex would be the lowest, right? So all we need to do here is find the solutions, all right, these vertexes by finding the solutions of the corresponding equations and then plugging those vertexes into this equation up here to find if it has a high value or low value. Now we would find these vertexes, like I said, by finding the solutions between two of the equations, right? This red and green vertex, green line, blue line, we'd find the solution between this blue equation and green equation. We'd have 1, 5. This vertex, solution between red and green, we'd find the solution between these two equations. This black one and this tall blue one would be this black equation, this blue equation, right? So piece by piece, you would find the solution of two linear equations. Pretty easy stuff. And then we have a list of vertexes. And we should plug them into here to see if we get a high value or a low value. The question will, of course, say we want to maximize or minimize. In this case, I did both. So in the minimization, the vertex I found was a 0, 2 vertex, and we got a 14. If you were to plug in all the vertexes, 14 would be the lowest value for z. And the maximization vertex was 6, 3. I plugged in 6 and 3, this vertex over here, and I got 51 as the maximization. So just a quick recap. You graph all the inequalities to find the bounding area. You want to find the vertexes of the bounding area by finding the solution between corresponding two equations. And then you plug those vertexes into the starting equation to get your maximum or minimum value.